All right, so let's take a look at molecular geometries, and this applies also to polyatomic ions, so shapes, three-dimensional shapes. The symbols we're going to use are A for the central atom, B for the bonded atoms, and I've seen either E or U or even X for lone pairs of electrons on the central atom. So here we're going to use U. Your book uses U, so we'll go with that. All right, let's start off with AB2. Let me draw that out for you. So it looks like that. We have the central atom and two atoms bonded to the central atom. Any molecule like this, or polyatomic ion, has the molecular geometry of linear. Electron geometry linear and molecular geometry linear. Next one, AB3. So central atom, three atoms bonded to the central atom. Let's draw that. So any molecule or polyatomic ion that has this structure is called trigonal planar for its geometry. Now there's one derivative, it's called, of the trigonal planar electron geometry. It's AB2U. Let's go ahead and draw that. So we have two bonds and one lone pair in the central atom. The electron geometry is trigonal planar, but the molecular geometry is called bent. Next up, we have AB4. Let's go ahead and draw that. Central atom and four atoms bonded to the central atom. So go ahead and draw these wherever you have room. I'm running out of room a little bit here, it looks like. So we have the central atom, four bonded atoms to the central atom. The molecular geometry and electron geometry, for that matter, are tetrahedral. There's two derivatives of the tetrahedral electron geometry, and by that I mean four electron groups on the central atom, but not all four are bonding pairs of electrons. Let's draw out AB3U, three bonds and one lone pair on the central atom. So anytime we have something like that, this is called trigonal pyramidal. Has a tetrahedral electron geometry, four electron groups on the central atom. Three of those are bonds. One of those is a lone pair, so trigonal planar molecular geometry. Another one is AB2U2. Let's go ahead and draw that up. Once again, the electron geometry is tetrahedral. That's why I call it a derivative of the tetrahedral geometry. But not all four electron groups are bonding pairs of electrons. We have two bonds and two lone pairs. The molecular geometry is called bent or angular. I use the term bent. I think your book or maybe Chem Honors book uses the word angular as well, but bent is fine for me. All right, next up, trigonal bipyramidal electron geometry. So AB5, go ahead and pause the video and draw that out. So again, be careful with this one. If you take a look on page 290 in table 8-1, you can kind of see this three-dimensionally. We have three bonds that go around the equator, and then one bond sticking up, one bond sticking down. So again, five bonds and no lone pairs. This is trigonal bipyramidal. We have three derivatives of the trigonal bipyramidal electron geometry. Next one is, so the first one I should say, is AB4U. Go ahead and draw that. So the lone pair occupies, and it has to occupy this particular spot, one of the equatorial positions. So not the axial sticking up, sticking down, but equatorial. And so we have four bonds and one lone pair. So this is a trigonal bipyramidal electron geometry. The molecular geometry, however, is called seesaw or irregular tetrahedron. I definitely prefer seesaw. All right, next one. Another derivative, AB3U2. Go ahead and draw that. Pause. This time, the two lone pairs will occupy two of the three equatorial positions. And so we have one bond sticking up, one bond sticking down, and one bond sticking to the side. This is T-shaped. One more derivative of the trigonal bipyramidal electron geometry, AB2U3. Go ahead and draw that. This one, the three lone pairs of electrons all occupy the equatorial positions. And we have one bond sticking up, one bond sticking down. Those bonding electrons are 180 degrees apart from each other. And we call this one linear. Next up, we have the octahedral electron geometries. First one, AB6. Go ahead and pause the video and draw that one. This one we have 6 bonds and no lone pairs on the central atom. Again, we can see that on page 290, how those electron groups are arranged around the central atom. We have 4 equatorial positions, and then the one sticking up, one sticking down. This is called octahedral. 2 derivatives of the octahedral electron geometry. First one, AB5U. Go ahead and pause the video and draw that one. For this one, I went ahead and took a bond off of the axial position at the bottom, made a lone pair there. And if you were to draw lines connecting the 4 bonded atoms, you would get a pyramid with a square base. Again, we can see this on page 316. A pyramid with a square base. This is called square pyramid. All right, one more derivative. AB4U2. Go ahead and draw that one. Pause, please. For this one, the lone pairs of electrons occupy the 2 axial positions. We have bonds along the equator. 4 bonds, 2 lone pairs. This is called square planar. So again, we have a couple tables in the book to show these kind of 3-dimensionally. Page 315, 316 for table 8.3. And then a summary of all of this on page 320 in table 8.4. So take a look there. All right, let's look at some examples of molecules and polyatomic ions and their molecular geometries. So instead of redrawing Lewis structures, we're going to go back to the Lewis structures we drew in the Lewis structure section of this notes. And then underneath each one, we will give at least the molecular geometry. I will go over electron geometries with you as well. So pause the video and go back to that page in your notes. All right, first Lewis structure we drew was carbon tetrafluoride, CF4. We have 4 bonds and no lone pairs on the central atom. This has a tetrahedral electron geometry, and more importantly, a tetrahedral molecular geometry. So for these, go ahead and pause the video if you need to write that name down underneath the Lewis structure so you can label each of these. Next, we did NCl3. We have 3 bonds and 1 lone pair on the central atom. So this also has a tetrahedral electron geometry. However, the molecular geometry is trigonal pyramidal. Trigonal pyramidal for NCl3. Next, H2S. Even though we talked about this before, we'll just pretend that the central atom does hybridize. Oh, let's go back. Let's label the hybridization of the central atom in each case as well. So what is the hybridization of carbon and CF4? Pause the video to write that down. It is sp3. Same question. What is the hybridization of nitrogen in NCl3? Also sp3. That's why both of them have a tetrahedral electron geometry. H2S, we'll just pretend that it forms hybrid orbitals, even though we know it does not. If it did, it would be sp3 hybridized. The electron geometry, tetrahedral. Molecular geometry is 2 bonds, 2 lone pairs. That is bent. Now F2 is a little different because there's no central atom, so any molecule or polyatomic ion that has just 2 total atoms will be linear. So fluorine is linear. Nevertheless, I guess the electron geometry around each fluorine would be tetrahedral since there's 4 electron groups. All right, be careful with this next one, HCN. This has 2 bonds and no lone pairs on the central atom. Notice what I'm doing there. I'm treating that triple bond as 1 bond. We'll see why later that's the case. It has to do with sigma and pi bonds. And so it looks like the angle between those bonds is 180, which gives rise to a linear molecule. So HCN is linear. Central atom is, because this molecule is linear, sp hybridized. That'll be important later on. Because carbon is sp hybridized, we get a linear molecule. O2, just like F2, is linear. Let's go down to AlCl3. We have hybridization. It is sp2 hybridized. Electron and molecular geometry, we have 3 bonds, no lone pairs. This is trigonal planar. SCl6, 6 bonds, no lone pairs on the central atom. This is octahedral. This is octahedral because the central atom is sp3d2 hybridized. Going down to NH4+, we have 4 bonds and no lone pairs on the central atom. The molecular geometry and electron geometry is tetrahedral. Hybridization of the central atom then, sp3. Be careful with this one here, SO3. We have 3 bonds, even though one of them is a double bond. 3 bonds, no lone pairs in the central atom. Therefore, this molecule is trigonal planar. Because it's trigonal planar, that tells us then that the central atom is sp2 hybridized. Again, that will be important later on. Sulfites, we have 4 electron groups around the central atom, 3 bonds and 1 lone pair. So this has a tetrahedral electron geometry, but the molecular geometry is trigonal pyramidal. Trigonal pyramidal, or better yet, tetrahedral electron geometry because the sulfur is sp3 hybridized. BeF2, 2 bonds, no lone pairs in the central atom. This is linear. This is linear because beryllium is sp hybridized. Let's take a look at C2H6, and for this particular one, we want to look at each carbon. Anytime you have a hydrocarbon such as this, look at each of the carbons in that chain to determine the geometry. So if we look at the carbon on the left, it has 4 bonds, 3 of those bonds, 2 hydrogens, and 1 bond to carbon. 4 bonds, no lone pairs. The geometry around each carbon then is tetrahedral. Each carbon then is hybridized, sp3. Xenon tetrachloride. We have 4 bonds and 2 lone pairs. So this has an octahedral electron geometry. The molecular geometry, though, is not octahedral because not all of those electron groups are bonding pairs of electrons. So this is 4 bonds and 2 lone pairs. So that's AB4U2. This is trigonal planar. Because the electron geometry is octahedral, that tells us that xenon is sp3d2 hybridized. IF3, 3 bonds, 2 lone pairs. So this has a trigonal bipyramidal electron geometry. The molecular geometry, however, is not trigonal bipyramidal. We have 3 bonds and 2 lone pairs. So this is AB3U2. The molecular geometry is T-shaped. Hybridization of the central atom, 5 electron groups. So this must be sp3d2 hybridized. So hopefully you got all of that. If not, go back, rewind, replay. I need you to label both the hybridization of the central atom in each molecule, as well as the molecular geometry. It's also helpful to know the electron geometry for each as well. All right, something else that's important is knowing the bond angles. So we've mentioned bond angles in linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral molecules or polyatomic ions. Nevertheless, if there's a lone pair of electrons on the central atom, the bond angles will not be as we described earlier. Here's why. Lone pairs of electrons occupy more space than bonding pairs of electrons because they are only attracted to 1 nucleus, while bonding pairs of electrons are attracted to 2 nuclei. Again, we can take a look in the book on pages 315 and 316, and we kind of see that. So the sticks in those ball and stick models represent the shared electrons, and then the lone electrons occupy this really big orbital. And so it's trying to show you that lone pairs of electrons occupy more space than bonding pairs of electrons. Consequently, the angles between the bonded pairs of electrons get squeezed together and are smaller in most cases. Let's take a look at, I'm going to start with ammonia, even though it's number 2. So let's go ahead and draw the Lewis structure for ammonia. Pause the video. So ammonia has a tetrahedral electron geometry, which would indicate 109.5 degree bond angles, same as any other tetrahedral molecule. However, since that lone pair of electrons is there, it pushes the bonding pairs of electrons closer together. As a result, those bonds are closer to each other than 109.5. In the case of a trigonal pyramidal molecule, bond angles are closer to 107.3 degrees. Let's go back to water. Go ahead and draw the Lewis structure for water. Pause the video. This time we have 2 lone pairs of electrons. And they're pushing those shared pairs of electrons between oxygen and hydrogen closer together. Definitely much closer than 109.5. So in a bent molecule such as water, bond angles are closer to 104.5 degrees. So just know when you have lone pairs of electrons on the central atom, it's going to push those bonding electrons or bonds closer together, and your bond angles are less than if there are no lone pairs of electrons on the central atom. All right, that concludes this video. Thank you for watching.